Right, this is a video just outlining question number 8 on page 105, just the solution. And again, if you've gone through it and you're successful with the answers in the textbook, then you can review this video and just make sure you're understanding all the little connections between each part. If you are at the point where you've read it and you're just not sure where to start and all the information, then I'm just going to kind of just briefly talk you through each section and what each section emphasizes and the process that you should go through. And again, next class we'll go over question number 8 if there are any more questions that you'd want clarified from the video. So question 8 is looking at a Camaro. The Camaro is traveling at 26.8 meters per second, and it has two braking methods. One is a skidding method and one is a non-skidding method. So question 8A is dealing with the non-skidding method. And what this means is that all the friction is happening within the brakes themselves. So you have what are called disc brakes, and you have calipers, and the calipers are pressing on those disc brakes, just like a bike. You have those calipers pressing on the rim of a bike wheel, and that's putting a force on that, and that's slowing it down. So that's where all the friction is occurring. However, as you stop, the wheels continue to move. So that's why we refer to this as a non-skidding braking. So you're going to calculate the acceleration for that section, remembering that the acceleration is going to be negative because the object is slowing down and the frictional force is going against the motion of the object. So the information that they give you is the initial velocity. They give you the distance that it's traveling, so it braked for, which is 39.3 meters. And you know that the final velocity is going to be 0 because it's coming to a rest. So when you have that information, you can eliminate time, right? Because time is not needed to perform this type of calculation. So this is where you're coming up with this equation. So this is just a review of kinematics. So when you use this equation, you're going to rearrange it for acceleration, and you're going to end up with 9.14 meters per second squared, rounded to the correct number of significant digits. You do want it, the textbook doesn't indicate this, but you should indicate any acceleration has a direction. So it is a backwards acceleration or a negative acceleration for that. So that's the non-skidding braking of the Camaro in the question. Then it goes on, and question B asks again for the non-skidding, and now it's asking for the frictional force. Now again, the frictional force is what's happening within the brakes themselves. So the wheels haven't locked, they're not sliding on the ground, but the wheels themselves keep moving, and all that frictional force is happening within the brakes themselves. And so you're going to calculate that by taking the mass of the car, which is 1,580 kilograms, and then you're going to multiply it by that acceleration rate that we calculated from part A. Right? So that calculation was done in the previous slide. So 9.13, again, I'm carrying the unrounded number because it is an intermediate calculation. And then I calculate the frictional force. Right, this is our extra digits. Rounded to the correct number of significant digits, we get 1.44 times 10 to the 4 newtons. And that just means that that's how much force was pressed on the brakes to cause an acceleration of 9.14 meters per second squared. And again, that would be negative, right? We're going backwards, or opposite to the direction of the motion of the car, object. So these are directly linked. This is the force that's causing this acceleration. And that's the key thing with this unit. You want to link motion to the actual force that's being applied. Question C now is looking at a skidding frictional force. So this is really sliding friction. So if you look in your textbook under all those frictional coefficients, those frictional coefficients are referred to as sliding friction. Two surfaces that are rubbing together. So to do this, I'm going to take you through a few steps. So the question's asking for, what's the frictional force, what's the acceleration, what distance does it go. So we're just going to go step by step on how you calculate that. So step one is calculating the normal force. Again, we're going to take the mass of the vehicle, acceleration to gravity. That's the force of gravity that is calculated from that. We know because it's a horizontal applied force that the force of gravity and the normal force are equal. So then we can come to the conclusion that our normal force here is going to be 15,484 newtons. Right? So again, that's dictated by the mass and the acceleration due to gravity. Once we have that, we can then go and calculate our kinetic friction using our frictional coefficient. Right? So this is from the textbook. So this number comes from rubber on asphalt. Right? So that number, that coefficient's been set. It's not something that you're calculating. It's something that will always be given to you in the question if it's needed, or you look it up on a chart that's provided for you on the test. So this number here is that coefficient. So that's the rubbing of the asphalt and the rubber. This year we calculated from the previous question our normal force. So we're going to rearrange that. So we're going to end up multiplying our normal force times our coefficient of friction. And then we're going to end up with 1.66 times 10 to the 4 newtons. Already you should be looking at this, and again, I can't emphasize enough, when you do these questions, you should start thinking about, okay, what do these numbers mean? Well, this number is a lot higher than that frictional force that we found when the car was being braked in a non-skidding situation. That was 1.44. So this is a higher frictional force. So already you should be anticipating that you're going to get a higher acceleration rate because there's a greater amount of force. And that's the way you always want to think of these kind of questions. So when you calculate your acceleration, you're going to use Newton's second law, F equals ma. Right? This is the rearranged. We know our F net. Our F net in this case is really caused by our frictional force. We calculated our frictional force from our previous section, from step 2. We're going to divide it by the mass of the vehicle, and then we end up with 10.5 meters per second squared. Now, once again, you want to stop and think, okay, does that make sense? Well, in this case it does. This has a higher frictional force. We're at 567.88 newtons. Well, that's a lot higher force than the 1.44 that we had in the non-skidding situation. Therefore, it makes sense that we have a higher acceleration. Again, the magnitude of the force is linked to the magnitude of the acceleration. Now, the question goes on and asks, okay, what's the skidding distance? So, once again, we know our initial velocity, we know our acceleration, we need to calculate our distance. Time is not needed, so that's why we're picking this. Again, that's our thought process for kinematics. And so we're going to rearrange that, and then we end up getting our 34.2 meters in distance. Which, when you go back to our original information, if you think back to our first question, the first part, that is a shorter distance than when it went as a non-skidding stop. Again, that makes sense. It is a higher acceleration, higher force. You're going to stop at a quicker rate. Now, the other part of the question was asking, I'm not going to do D because D is just going through the same process but on ice, and ice is slippery, low frictional coefficient. You're going to go a lot longer ways, really low acceleration. You can figure that out if you want, but I'm not going to go through that particular answer. But E is an important one because it's asking you, does mass really affect the skidding distance or the acceleration rate of the object as it's sliding to a stop? And the answer simply is no. And to prove this, what I would like you to do is go back to question C and then just change the mass, right? Change to 2,000 kilograms. And what you'll find is that when you do your initial calculation, so if we go back a couple steps here, when you calculate your normal force, you're using that 1,580 80 kilograms, and then you end up dividing it out again, and you're going to find that if you substitute with a 2,000, and I would like you to go through that process, put in the 2,000 instead of the 1,580, and you calculate it, and you'll find that you will multiply it by that 2,000 in one step to find that force of friction. And then you're going to, in order to find your acceleration rate, you're going to divide it out again. So it's the same factor being multiplied and divided. So it really crosses out. It's like crossing out units. But it's worth going through that process and just working through it to see what happens. And you'll find that you're going to end up with 10.4 meters per second squared. So the reality is if you took that Camaro and you loaded up with a bunch of friends and made that mass really high, and you traveled at the same speed, and then you braked hard and locked those wheels so you slid to a stop, it would make no difference in that acceleration rate, because mass gets canceled out. It's multiplied in one section, it's divided out in the second section. Go back to question C, try it, see it for yourself, because it's a good thing to verify, and it is a good shortcut to know for other questions. So again, after reviewing this video, come in with questions next class to clarify any ideas, and then we can work through it together as a class and just clarify any concepts.